Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss how to determine the coefficient of viscosity by rotating cylinder method. In our previous video lectures already we have discussed regarding this calculation of coefficient of viscosity by different methods like capillary tube method and falling sphere method. So today another method we are going to discuss, which is known as rotating cylinder method. So for this, we have taken this diagram, and in this if you see, there is an outer cylinder is there. This is the outer cylinder and this is the inner cylinder of this, and in between these two cylinder, outer cylinder and inner cylinder, we have a liquid which is present, or the fluid which is present, and the viscosity of the fluid need to be measured. Okay, so this is the viscous fluid. Here is the viscous fluid which is present between these two cylinder, and viscosity of the fluid need to be determined. Okay, now these two cylinders, if I draw in in a separate diagram, like it will be present in this way. You can see this is one cylinder, and this cylinder is present over another one cylinder is there, which is like this. Okay, and this cylinder is fixed with you can say there is a shaft is connected here, or we can say there is a pulley type is there for this two for rotation purpose. And this cylinder actually, this cylinder is stationary, and this cylinder is connected to a torsional spring here. This is the spring which is connected to this, and this cylinder will be our constant. That means it is not going to rotate. So the outer cylinder of this part is going to be rotated. That means this one, this outer cylinder is going to be rotated, and the outer cylinder is connected, as I told, like with a pulley or some kind of shaft is connected to this one, so that it will be rotated in this direction. Okay, now, so as I told that between these two cylinder, the fluid which is present, that viscosity need to be calculated, and the radius of this inside cylinder, this one, is R1, and the outer cylinder is R2. So what are the terms can be considered here? One we can consider R1, and second one we can consider R2. Next is the distance between these two layers, or the distance between this inner cylinder and the outer cylinder, this height h. So that can be also considered. And next is viscosity of the fluid which need to be measured, that is mu. And next, this is the h, height of this liquid in this inner cylinder, you can say, that is capital H, we can mark it. And any other thing is there? Yeah, torsional spring, the torque need to be measured here, so we can consider the T is there, the torque which is acting on the cylinder need to be measured. So before going to this derivations of this viscosity, so I'll give just a small brief about this, like how it is, So this shaft or this pulley which is connected to this outer one, this is going to be rotated. Okay, so when this is going to rotate, so along with this, the liquid which is present here, the fluid which is present here, that also going to be rotated, but this cylinder is going to be fixed. Okay, so when this liquid is going to rotated, we know that the viscosity is nothing but the resistance to flow, or resistance of a fluid which is supposed to be flows, you can say, like means when the liquid is flowing or when the fluid is flowing, and it shows its resistance to flow, so that is viscosity actually. And so that when it is liquid, when this fluid is rotating, so if the viscosity of this fluid is having a suppose high viscosity is there, okay, then we can say this cylinder or this outer cylinder is going to be rotated very slowly. If the fluid viscosity is less, very less, then you can rotate very fast. So that's why it is the resistance of a fluid for flow. So this one, this viscosity part already we have discussed in our previous lectures. So this one, that one we can follow. Now here we'll identify this mu. Okay, before going to that, let me tell you what are the other things are there. So as I told you, this is R1 and R2 is there, and apart from that, we have a h, capital H and small h, and the omega is there. Omega is the angular velocity, you can consider angular speed of the outer cylinder, we can say. Omega is the angular velocity of the, or angular speed of the outer cylinder, how it is rotating. Okay, now yeah, so what are things, let's find out. Now as I told you, this omega is the angular speed of the outer cylinder. Now we need to find out the tangential speed of the outer cylinder. What is the tangential speed, or you can say the peripheral speed of the outer cylinder? So that one we can write the tangential speed. So we can write the tangential speed of the outer cylinder is nothing but, we can just write at what speed it is rotating with respect to its radius. So radius is of the outer cylinder is nothing but, that is R2. So we can write R2 here. Okay. Now before this, actually, if you see the torsional spring which is connected here, okay, so that torque here, as I told you, the torque T is there. So the torque T acting on the inner cylinder, okay, and that will be measured with the help of torsional spring. Already I told, I think. So that's why T is considered here. And the torque on the inner cylinder, okay, the torque on the inner cylinder, it should be, must be equal and opposite to the torque which is applied at the outer cylinder. Okay, so the torque which is applied, or which is, you know, acting on the inner cylinder. So how the torque can be applied? Now see, when it is, this fluid is be started rotating, so that will be give an impact on this inner cylinder. So the torque which is acting on the inner cylinder, and that to be, we can measure with the help of torsional spring. So that should be equal and opposite to the outer cylinder. This one, torque of outer cylinder. T2 we can consider this one. Okay. Now tangential speed I have written omega into R2. And next we can write the tangential velocity of liquid layer in contact with the outer cylinder. So the tangential velocity, you can write tangential velocity of liquid layer in contact with outer velocity will be equal to the tangential velocity of the outer cylinder. So tangential velocity of liquid layer in contact with, so this is the liquid is there. So what is the tangential velocity of this liquid layer? That will be equal to the tangential velocity of the outer cylinder. So velocity of liquid layer is equal to the, we can write tangential velocity of outer cylinder. Okay, so this one we can write. So before going to that, let's find out the velocity of liquid layer, the velocity of liquid layer at outer cylinder, liquid at outer cylinder. So this one we have already identified is tangential speed, what was there. So here also the velocity of the liquid layer at the outer layer, we can write omega into R2, omega into R2. Okay, now this is about the outer one. Similarly, the velocity of the liquid layer, the velocity of liquid at inner, this is outer cylinder and this is for inner cylinder. So inner cylinder, actually this one will be actually 0. So why it is 0, let me tell you. If you remember the Newton's law of viscosity, what we have studied, so when the liquid is flowing, you know, we have seen this, we have taken the layers, okay, and the layers, how the velocity gradient was there, like, you know, it was like this. Okay, that means if you see this one, so the force which was acting on this, the force which was acted on this, and the velocity at different layers, you can see this maximum velocity you got here, then slowly it was decreased, and at this point we have the velocity of 0. Okay, and as the thickness was increased, as the layers was increased, okay, we got the velocity gradient, that is, you know, del u by del y we have taken there. And here also, you know, with change in distance del y, and with respect to here at this level what is the velocity, and this level what is the velocity. Now if you come to the bottom level here, this level at this point, due to the friction, internal friction of this, we will consider the viscosity of this liquid is 0. So slowly it is going to be increased. So here also same thing, when the liquid which is present between these two cylinder, okay, now at this point we have a, now you see this is not a solid one. So if it is solid one, that is different. Now this part is a liquid one. So solid is there means all everywhere the molecular strength or the intermolecular forces between these molecules are constant or same, you can say. But as this is the liquid one, okay, everywhere the molecular bondings are different. And here if you start rotating at this point, so at this point we have a different angular velocity will be there, at this point we have a different angular velocity will be there. Okay, so all the points we have different angular velocity. So now as this is rotating, so near to the cylinder part we can say that a high velocity is there, or how a high angular speed is there. And at this point of this inner cylinder part, we have that the velocity will be, velocity of the liquid in the inner cylinder part will be 0. Okay, so that much movement will be not there. That's the same concept. If you see from here, you can understand this concept also. So that's why I have written velocity of the liquid at the inner cylinder is 0. Now we can find out the velocity gradient, as I have written the velocity gradient over the radial distance, over the radial distance. So this one we can write, radial distance is nothing but r2 minus r1. So r2 is the outer radius and r1 is the inner radius. Now the velocity gradient we can write, we know that du by dy, and here du is the difference of velocity. So one is, you know, the outer velocity what was there, velocity of the outer one, so that is nothing but omega r2. And as I told, the inner one, that inner cylinder was there, so that is 0. Okay, because that surface, near to the surface we need to consider. So at this level most of the velocity will be 0, so 0 into this r1, that will be 0. And this dy is nothing but the distance, like, you know, the difference of this distance, at what distance we have considered, like from this point to this point. As here we used to consider at this layer, and this is the layer, so that was the difference or distance we can say, or thickness we can say. So here also the same thing, so that is nothing but r2 minus r1. Okay, now this one we can write omega r2 divided by r2 minus r1. So this one we can write equation 1. Now as I told, this is the Newton's law of viscosity. So that equation also says that as per the Newton's law of viscosity, we can write tau equal to mu into du by dy. So as this formula says, or this concept says, this equation, so what I'll do, just I'll put this value here. So I can write mu into omega r2 by r2 minus r1. So this one we can give equation 2. See here our intention is to find out the coefficient of viscosity. So this is the, like, you know, basic steps or primary steps of this experimental work, or you can say the setup which is there. From here we can identify the viscosity. So before going to this derivations, we need to understand the theory part of that. So that's why I have explained in that way, so that you can get some at least little idea. So now why I identified this shear stress, because next, see here we need to identify the torque, and for calculating the torque we need to know what is the shear force. Again, for calculating the shear force we need to know the shear stress. Okay, so that's why here we have calculated already, the identified the shear stress value. Now Once you identify the torque value, then we can go for the finally in this torque equation we have this terms mu, viscosity term is there. Anyway, so this is the equation. Now here I can write one more thing, as I told, shear force. So shear force equal to, I can write the shear stress into the area. So area of the surface. What is the area of the surface here? Okay. So this area of the surface of this, you can see the total area of the surface which is connected to this liquid. So total will be not considered up to here only. Okay. So now tau already we got the value here, mu omega R2 by R2 minus R1. So what about the area? Now area of the surface, actually the shear stress which is acting on the surface area. So what is the surface area is there? Now surface area is nothing but 2 pi r h, 2 pi r into h. So pi r means what? Now which are this inside cylinder r, this is the r. Okay, so this one, and here it is R2, and this one we can write 2 pi R1 H, and this one we can give equation 3. Yeah. So next we can identify, okay, up to what? So shear force calculated. Next we can write the torque. Okay, the torque T1, the torque T1 on the inner cylinder, the torque T1 on the inner cylinder, the torque T1 on the inner cylinder, and this is due to, you know, this is due to shearing action. You can write this is due to shearing action on the liquid in the annular space. Shearing action of the liquid in the annular space is, we can write T1 equal to torque, we can write shear force into the radius. So shear force into radius, which radius? Inside radius R1. Okay, so now shear force already just now we have calculated. The formula is mu omega R2. Yeah, mu omega R2 by R2 minus R1 into area was there 2 pi and 2 pi R1 H into, again R1 is here, so R1 we can write R1 square. Okay, so this one we can give equation 4. Equation 3 completed, equation 4 now I can give. Now this is one term. Now here if you see, again you go back to this diagram, this is the diagram is there. In this diagram, if I already told you, this is the H. So if the gap between the bottom cylinder, this is the bottom cylinder, and the inside cylinder, the gap between the two cylinders is H, then the torque which is applied on the inner cylinder, okay, it can be written. You see the torque which is applied on the inner cylinder, so that is actually different. So already this equation we have identified. Just I'll write the equation, or you can say, yeah, no, inside cylinder already calculated, I think. Yeah, torque on the inner cylinder due to the shearing action already we have identified. Now we need to see the torque of the which is applied on the inner cylinder, and here we need to calculate the outer cylinder actual torque. Okay, the outer cylinder, what is the torque is there, we need to identify. So here we can write the torque at the outer cylinder, that is T2 equal to mu by 60T, mu by 60T into one formula is there actually, pi square into n into r to the power 4. Okay, so this one actually we have derived previously, from that we have taken this. Okay, so this is the torque on the outer one. And now here if you see I'm talking about the torque at the outer one. Okay, but here if you see, this is the torque applied on the inner cylinder. Now if you see, how the torque was applied, and in the torsional spring which is connected to this inside cylinder. So the torque was applied on this inner cylinder. Okay, so the torque generated here, so because from here, from this torque we will we'll identify the torque at the outer one. Okay, because I told in the starting, the torque which is applied on the inner cylinder, that is going to be equal and opposite to the torque of the outer one, T2 one. Okay, so that's why the torque, or you can say the applied on the inner cylinder, that can be considered T2, is given by this equation. Already we have done previously, so directly I have taken that equation. Now here R we need to consider, let's consider R1, and the T is nothing but the thickness between these two. Okay, so T equal to, we can consider H. Just put this value in this equation, we can get it. So T2 equal to, just write mu by 60H, and this is pi square. And one more thing, one more term is there, N also you can write here. Okay, later I'll put it that one. So let now write down pi square N, and this is R1 to the power 4. Okay, now as we know that, here also you can put it actually. So we know that omega equation is nothing but 2 pi n by 60. So this is the omega equation is there. So now here, if you want to identify the n value, then we can write 60 omega by 2 pi. So here you can put the value of n. So what will get? Mu by 60H pi square, and here 60 omega by 2 pi R to the power 4. Now 60 is cancelled, pi is going to be cancelled, only one pi will be there. And so finally what we are going to get here, now T2 equal to, we can write pi, here pi omega R1 to the power 4. Pi, mu is there, so mu, write it here, mu pi omega R to the power 4, R1 to the power 4 divided by 2 H. Pi cancel, this pi is cancelled, so 2H. So this is another equation. We can write equation 5. Okay, this is equation 5. Now here T2 we have identified. Now the total torque we need to identify here. Okay, so now write down the total torque which is acting on the inner cylinder, okay, is, we can write T equal to T1 plus T2. Now see the total torque acting on the inner cylinder, that means, but the inner cylinder, this is the inner cylinder is there. Now this inner cylinder is, you know, impacted by the outer cylinder, as I told you. So outer cylinder torque we have identified now. Okay, this outer cylinder torque we have identified, and the inner cylinder torque also, due to the impact of this liquid, also we have calculated that one. Okay, now total torque, which is total torque acting on the inner cylinder, is equal to T1 plus T2. So now we can write here what the equation, we can write T1 value, what is there? T1 value is here. So we can write this mu omega R2 divided by R2 minus R1 into 2 pi R1 square H, and plus this is the T2 term is there, that is mu pi omega R1 to the power 4 divided by 2H. I hope this is the equation is there. Yeah, now what we'll do, we'll just take some common things from here. So T equal to, I can write here. So what are the common things I can consider? 2 pi mu 2 pi, yeah, mu, anything is there, omega Yeah, omega also. So omega we can also consider, and r1 square also you can consider. See, r1 to the 4, r1 square is there. So what I'll do, 2 pi mu omega and r1 to the power square. Take this common, and then what will the pending will be there? Like what are the remaining terms will be there? RH, R2H will be there. R2 and H will be there. R2H divided by this one, R2 minus R1. This is R2H divided by R2 minus R1 plus, again that side what will be there in this side? Already this one gone, mu gone, omega gone. So pi, yeah, pi also I think we have taken. Yeah, pi also taken. Then r1 to the power 4, r1 square gone, then r1 square only. So only r1 square by, here we have taken 2 also common, I think we have taken. So 2 common taken means, so here 2 is not there. So 2 multiplied, 2 divided. So 2 into 4, so 4h. So this one we can write r1 to the power 4 divided by 4h. This is the equation. Now what I'll do, actually what is our intention? Now our intention is, okay, let solve this one. So what I'll do, 2 pi mu omega r1 square, and here let write this one, multiply of this r2 minus r1 bracket close into 4h. Here in the top we can write 4h r2h plus r1 to the power 4, and here r2 minus r1 bracket close. Okay, now here actually what is our intention? We need to find out the value of viscosity. As I told, mu value we need to calculate. So I'll keep mu one side, and remaining term I'll take it to other side. That means here I can write this T into here 2, this 4h will be gone there. That means let's take it here, 4h r2 minus r1 bracket close. Then here we can consider this is 2 pi mu omega r1 square bracket start. We can write this total whole term, we can write it here. That means 4h r2 h plus r1 to the power 4, again bracket start, r2 minus r1 bracket close. Now here 4 is there and here 2 is there, so 2h we can write. So finally what I'll write, just I'll write final equation. This is 2h and t also you can write 2ht. This is r2 minus r1 bracket close, and denominator again we can write it is pi mu omega r1 square, and again bracket start, this is 4h capital H r2 plus r1 to the power 4 bracket again start, r2 minus r1 bracket close. So this is the final equation of viscosity. Equation 5 gone. So this one we can give equation 6, and this is the equation of coefficient of viscosity which was identified from this concept, and that concept is nothing but rotating cylinder method. So I hope you understand this concept, or how to determine the coefficient of viscosity. Yeah, this is all. If you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you all.